In this video, we're going to introduce the squeeze theorem and do a few examples. So the squeeze theorem says that essentially if a function h of x is in between two functions that both have the same limit as x approaches c, then the limit as x approaches c of h of x is also the same limit. So more formally, if for all x in some open interval containing the point c, f of x is less than or equal to h of x, which is less than or equal to g of x, and the limit as x approaches c of f of x is equal to the limit as x approaches c of g of x, which is equal to L, then the limit as x approaches c of h of x is also equal to L. So here we've got it down here in a picture. Our red function is the function h of x that is squeezed between f of x and g of x. And notice that it is squeezed between h of x and g of x over some interval containing c, but not necessarily everywhere. So over here, h of x is escaping g of x and h of x, and that's okay as long as there is some interval containing c over which h of x is between those two functions. It's also required that over that interval, f of x is less than g of x, or the other way around, but it's okay again if they like switch places at some point. That's okay. It doesn't have to be that f of x is less than or equal to g of x everywhere. It just must be true again in that interval containing c. So let's look at an example. Let's look at the example limit as x goes to 0 of x squared times sine of 1 over x. So we've seen the function y equals sine of 1 over x before. Back when we talked about situations where limits did not exist, we had this example and we saw that the limit as x goes to 0 of sine of 1 over x does not exist because right around 0, this function starts to oscillate wildly between -1 and +1. But we still will be able to argue using the squeeze theorem that the limit as x approaches 0 of x squared times sine of 1 over x does exist. So to do this, we've got to find functions f of x and g of x such that f of x is less than or equal to the function we're interested in and g of x is bigger than or equal to the function we're interested in over some interval containing 0. So over interval containing the limit that we're interested in 0. So this is over some interval containing 0, not necessarily everywhere, but over that interval. And it's also got to be true that the limit as x approaches 0 of f of x is equal to the limit as x approaches 0 of g of x. So let's think about how we could find those kinds of functions. So the squeeze theorem is always going to be based on the fact that the function we're interested in is bounded by two other functions. In the example of sine of x, we know that sine of x is bounded between 1 and -1. So sine of x, no matter what, is bounded between -1 and 1. It can never be larger or smaller than those values. And so, you know, the thing in here could be complicated. So we could have, instead of just x, we could have, 20 times x over 4 or whatever, and it would still be bounded between -1 and +1. So that anything, 1 over x includes as something that could be, that works. Sine of anything is bounded between -1 and +1. So we know that this is true. Now what do we need to do? We need to make this expression right here look more like this expression right here. So we've already got the sine of 1 over x. To make that look more like the function we're actually interested in, we can multiply that equation by x squared. And so now we've got -x squared is less than or equal to x squared sine of 1 over x, which is less than or equal to x squared. So I multiplied each term here, each term in that string of inequalities by x squared. Okay, great. Now I've got a potential function f of x and a potential function g of x, where x squared sine of 1 over x is bounded between those two functions. Let's consider the limit as x goes to 0 of negative x squared. What happens to that? Well, that's just a polynomial, and so we can just plug in the value. That's negative 0 squared, and that's 0. And similarly, the limit as x goes to 0 of x squared, we can just plug that in too. That's 0 squared, which is also 0. And so, what do we have? So, limit as x goes to 0 of negative x squared is equal to the limit as x goes to 0 of positive x squared. They're both equal to 0. And negative x squared is less than or equal to x squared sine of 1 over x, which is less than or equal to x squared. And so now we've got the two requirements that we need for the squeeze theorem. We've got that x squared times sine of 1 over x is squeezed between negative x squared and x squared. We could sort of draw a picture of that if we wished. So we could draw a picture. We know what x squared looks like. That's a parabola pointing upwards. We know what negative x squared looks like. That's a parabola pointing downwards. And then we don't know exactly what x squared sine of 1 over x is doing. But whatever it's doing, it's got to be doing something where in the middle it is squeezed between x squared and negative x squared, and therefore it has the same limit as those other two functions as x approaches 0. So by the squeeze theorem, it's sometimes also called the sandwich theorem, the limit as x approaches 0 of x squared sine of 1 over x is also equal to 0. And we are done. And if we wanted to write up that solution nicely, above we were thinking through and doing our work, but a nice solution, this was for homework, like writing up a solution, might look something like that. So up above we had to think about, what is f of x, what is g of x. We had to do some creative thinking to figure that out. But once you've got all your scratch work done, you then want to write up a nice solution, something like this, that shows all the information needed without the messy stuff. Okay, let's do another example. Suppose that 1 is less than or equal to f of x, which is less than or equal to 1 plus x squared over 6 for all values of x near 0. Find the limit as x approaches 0 of f of x. So here we know a lot less information. We just know ahead of time that f of x is squeezed between two functions. And let's think about the behavior of each of those functions as x approaches 0. So 1 is a constant. We know that the limit as x approaches 0 of 1 is 1. And what else do we know? So the other function, limit as x approaches 0 of 1 plus x squared over 6. What happens to the limit of that whole thing? Well, the limit of the constant 1 is still 1, plus the other part is a rational function, we could think of it as, but the denominator is not 0, so we can just plug 0 into it. So 0 plus 0 squared over 6, and 0 over 6 is 0, so that's 1 plus 0, or 1. And so we know now that f of x is squeezed between two functions that both approach 1 as x approaches 0. So since 1 is less than or equal to f of x, which is less than or equal to 1 plus x squared plus x over 6, and limit as x approaches 0 of 1 is equal to the limit as x approaches 0 of 1 plus x squared plus x over 6, are both equal to 1 by the squeeze theorem. So by the squeeze theorem, the limit as x goes to 0 of f of x is also 1.